This is video 2 for lesson 2 in unit 9, weak acids and bases. So in our previous video, we looked at what is a weak acid, what is a weak base, and we went over some new equations that we are going to use for pKa, pKb. We talked about what Ka and Kb are and where to find those values if needed. So now we're going to start looking at example problems. So our first example problem, we are looking for Ka and pKa from equilibrium concentrations. So what that means is we are given the concentrations at equilibrium, so after the weak acid or base is partially ionized. So what we're going to do is look at the problem. We have nicotinic acid. It's weak and it's monoprotic. Monoprotic, remember, means that it has one H. What are the values of Ka and pKa if we're given these at equilibrium? So if you see this phrase here at equilibrium, we don't have to do any long sort of problem. We just have to plug in values. But in all of these problems, if it is a weak monoprotic acid, we can use this general equation because we don't even have to worry about what nicotinic acid is. All weak acids are going to follow this general formula. So the weak acid with an H with its anion plus water, and we get the conjugate base and we get the conjugate acid. So water, or H3O plus, sorry. That should be H3O plus. So we get the conjugate acid and the conjugate base. So it really doesn't matter what that is because A minus really doesn't matter all that much. So with that, if we are already at equilibrium and we have our general equation here, and we know at equilibrium, this is how much we still have left over, 0.490. And we know that this is partially ionized and given us 8.40 times 10 to the negative fourth molar H3O plus. Because these two are in the same mole ratio, that means that we also have the same amount of A minus. So Ka of this up here, this general form, is going to be the concentration of A minus times the concentration of H3O plus, all over the concentration of what remains from our partial ionization of HA. So we have those three things. Remember that water is a pure liquid, so we do not count that in equilibrium calculations. So our Ka value is going to be 8.40 times 10 to the negative fourth times 8.40 times 10 to the negative fourth. So there are our A minus and our H2O plus all over 0.490, which is our concentration of HA. So this is our equilibrium value. So if we did an ice chart, this would be that last row across. And so when we calculate this out, we should get 1.44 times 10 to the minus 6. So that's one of our answers. So remember Ka, Kb, no units. And then pKa is a negative log of that. And that gives us a pKa of 5.84. Again, no units on pKa or pKb. Now, our second example. We are going to calculate Ka, but we're given a percent ionization and a molarity of our solution. And we want to calculate Ka and pH from this. Now, this is going to involve an ice chart, but we're kind of going to go in reverse with this one. If we know how much is ionized, we know that percent ionization, which in this case is 4.20, is a concentration of H3O plus over our original concentration times 100. So we can use the percent ionization formula to calculate what this value is going to be. So how much H3O plus ionizes? Well, when we calculate this, we get 4.20 times 10 to the minus third molar H3O plus. Now, we can use that to figure out pH. And we get a pH equal to 2.38. So there's one of our answers. But to calculate Ka, we have to go and work backwards in our ice chart. So we know this value here, our original concentration of acetic acid, our HA. We know that initially we're not going to have any of these. But we know that it's 4.2% ionized. 4.20% of 0.1 is this value that we calculated here. So that's our equilibrium value. And that will be the same for A minus. So from that, we know that this is always going to be minus x and these are going to be plus x, but we know what x is. So this is plus 4.20 times 10 to the minus third, and this is plus 4.20 times 10 to the minus third. So when we go back, we know that this value is minus x. Well, we know what plus x is. So this is minus 4.20 times 10 to the minus third. So when we do this calculation, we get 0.0958. Now we can use these three values at equilibrium to calculate Ka, because Ka is the concentration of A minus times the concentration of H3O plus all over the concentration of HA at equilibrium. So we end up at 4.20 times 10 to the minus third times 4.20 times 10 to the minus third all over 0.0958. And that gives us 1.84 times 10 to the minus fourth for our value of Ka.